Hello, we're now at the last section of this video course, Controlling Network Communications. In the previous section we saw about process domains and file level access controls. In this section we'll learn how network access controls are governed by SELinux. We'll then cover what administrators can do to further strengthen network communications using IP tables, and describe how SELinux policies can be used for cross-system security through. We'll finish this section with an introduction to CPISO labeling and its integration with SELinux.
Now we move on to the first video of this section, from IPC to TCP and UDP sockets.
In this video we're going to take a look at using shared memory and communicating locally through pipes. We'll then move on to understand netlink sockets and how to deal with TCP and UDP sockets. Lastly, we'll look at listing communication contexts. One of the features provided by SELinux is the ability to control network communications. Linux applications communicate with each other either directly or over a network. But the difference between direct communication and networked communication from an application programmer's point of view is not always that big. Let's look at the various communication methods that Linux supports and how SELinux aligns with them. So, to start with, let's have a look at the most basic thing, that is using shared memory.
The method that is the least network-like is the use of shared memory.
Applications can share certain parts of the memory with each other and those shared segments to communicate between two or more processes. To govern access to the shared memory, application programmers can use mutual exclusions or semaphores. A semaphore is an integer that is atomically incremented or decremented, whereas a mutex can be interpreted as a special kind of semaphore that only takes the values 0 or 1. On Linux, two implementations exist for shared memory access and control, sysv style and POSIX style. We'll not dwell on the advantages and disadvantages of each, but rather look at how SELinux governs access to these implementations. SELinux controls the sysv-style primitives through specific classes, sem for semaphores and shm for shared memory. The semaphores, mutexes and shared memory segments inherit the context of the first processes that creates them. Here's an example AVC denial for a sysv semaphore-related communication failure. Now, administrators who want to control the sysv-style primitives can use the various IPC commands. With IPCS, the current sysv-style primitives, such as shared memory segments and semaphores, can be listed with IPCRM. These shared memory segments and semaphores can be removed or destroyed. With IPCMK, new shared memory segments and semaphores can be created. For instance, let's first list the resources and then remove one of the semaphores. Type at the terminal IPCS and enter. Let's use this semaphore. So, when POSIX-style semaphores, mutexes and shared memory segments are used, SELinux controls those operations through the file-based access controls. The POSIX-style approach uses files in the directory, dev shm, which is simple for administrators to control and manage. Now let's have a look at communicating locally through pipes. A second large family of communication methods in operating systems is the use of pipes. As the name implies, pipes are generally one-way communication tunnels with information flowing from one or more senders to one receiver. Another name that is often used for a pipe is first in, first out. We have two types of pipes in Linux: anonymous pipes, also known as unnamed pipes, and named pipes. The difference is that a named pipe uses a special type of file in the regular file system as its identification, whereas anonymous pipes are constructed through the applications with no representation in the regular file system. In both cases, SELinux will see the pipes as files of the FIFO_file class. Named pipes will have their path associated with regular file system and are created using the mknod or mkfifo commands. Anonymous pipes, however, will be shown as being part of the pipefs file system. This is a pseudo file system, not accessible to users but still represented as a file system through Linux Virtual File System or VFS abstraction. There are two denials associated with FIFOs. Let me show you these. First, I changed the root directory with the cd command. So the first one is a named pipe with this path, which I gave just now, while the second one is an anonymous one. Notice how the second is shown to be part of the pipefs device. From an SELinux policy point of view, access control is handled on the FIFO file level. Two domains that both have the correct set of privileges towards the context of the FIFO file will be able to communicate with each other. Administrators can find out which process is communicating over FIFOs with other processes through tools such as ls or by querying the PROC file system as part of the PROC CPID FD listings, which you see here. For instance, here's the snippet from LS, which shows the pipe-based communication setup between two POSIX-related processes. The node column shows the FIFO identifier, which is the same for both processes. Now, let's move ahead to understand netlink sockets. A special case of Unix domain sockets are netlink sockets. These are sockets that allow user space applications to communicate and interact with kernel processes. Unlike regular Unix domain sockets, whose target context is associated with the owner of that socket, netlink sockets are always local to the SELinux context. In other words, when a domain such as sysadm_t wants to manipulate the kernel's routing information, it will open and communicate with the kernel through a netlink root socket, identified through the netlink root socket class. Let's run an search command to elaborate this. As applications gain more features, it might be that some of these features are no longer allowed by the current SELinux policy. Administrators will then need to update the SELinux policy to allow the netlink communication. An overview of supported netlink sockets can be devised from the netlink information in its manual page. Let's view this by executing the command man space netlink and enter. So, this is the manual page for netlink. For instance, the netlink XFRM socket is supported through the SELinux netlink XFRM socket class. Cool. Now, let's explore about dealing with TCP and UDP sockets. When we go further up the chain, we look at socket communications over TCP and UDP sockets. In this case, rather than the communication being directly between processes, the flows are to and from TCP and UDP sockets. SELinux will assign types to TCP and UDP ports as well, and these types are then the types to use for socket communication. For SELinux, a client application connecting to a DNS port uses the name_connect permission over the TCP_socket class toward the typed port. For UDP services, the name_connect is not used. Daemon applications, on the other hand, use the name_bind privilege to bind themselves to the port. Administrators can fine-tune which label is assigned to which TCP or UDP port. For this, the semanage port command can be used. For instance, to list the current port definitions, here's the command which you could use. semanage port -l. So, here's the list of ports. In this example, we see that the HTTP port_t label is assigned to a set of TCP ports. Web server domains that are allowed to bind to HTTP port T are, as such, allowed to bind to any of the mentioned ports. To allow a daemon, such as an SSH server, to bind to other or additional ports, we need to tell SELinux to map this port to the appropriate label. For instance, to allow the SSH server to bind to port 10122, we first check whether this port already holds a dedicated label or not. This can be accomplished using the sepolicy command, which is part of Policy Core Util's devel package in RHEL. Let's execute the command sepolicy network-p10122, which are the values which you get for TCP and UDP unreserved ports when you execute this command. The unreserved port_t label is not a dedicated one, so we can assign the SSH port T label to it. Let's use the next command for this purpose. So you could see that it says that SSH port_t is already defined. When a specific port type is already assigned, then the utility will give this error, which we got here. If this is the case and another port cannot be used, then there is no other option than to modify the SELinux policy. Finally, let's see how to list connection contexts. Many of the tools in an administrator's arsenal are able to display security context information. Like with the core utilities, most of these tools use the -Z option for this. For instance, to list the running network-bound services, netstat can be used. Here's how you could use it. Even ls displays the context when asked to. Another advanced command for querying connections is the ss command. Just calling ss will display all of the connections of the current system. When adding -Z, it adds context information as well. For instance, here's the command which queries for listening TCP services. Superb. More advanced queries can be called as well. Consult the SS manual page for more information, which you can get by executing man ss enter. Awesome! In this video we looked at the various communication methods that Linux supports and how SELinux aligns with them.